Now we will go to our last topic, which is the partial differential equations. Okay, partial differential equations, and we can call it PDE. Before we talking about the partial differential equations, the type, the solution, what kind of physics can drive different partial differential equations, I want to give a brief motivation why we learn about partial differential equations. Okay, so a lot of physical phenomenon in our real life is derived from partial differential equations. For example, we have the temperature as function of the space and time heat transfer. Okay, is a type of partial differential equations. So motivation. One example is heat transfer, which is temperature as function of space and time. Okay. We also have fluid flow. So Navier-Stokes equation is one type of the partial differential equations. Okay. And we can also have electromagnetic wave as function of space and time. Electromagnetic as function of space and time. So another example can be non-linear Schrödinger equations or time-dependent Schrödinger equations. Time-dependent Schrödinger equations. And you can get electronic waves as function of space and temperature. And there are more examples, for example, vibrations, the string. When you have a string, you have the vibrations of the string that is also as function of space and time. So vibration. So there are many examples can derive partial differential equations. Then learn partial differential equations, get the definition, get the type of the partial differential equations, how to derive the physics to partial differential equations, how to solve the partial differential equations are very important topic. Okay. So today we will give a brief introduction of different types of the partial differential equations, and we will talk about what kind of physical phenomena can derive those types of PDE and how we can solve it. And we will probably, if we have enough time, we will probably solve each type of the partial differential equations. Okay. So what is PDE? The definition. The definition of the PDE. The big difference between the PDE and the ODE is that the PDE is a multivariable function, and the derivative and the partial derivative of that multivariable function. Okay, so a PDE is an equation relating multivariant function. We can say this is function u and various partial derivative of that function u. So the big difference between the PDE and ODE is as function of one single variables, but PDE is equations related to multi-variable function U and various partial derivative of that function. So let's make an example of a partial differential equations. Example, we have this U, which is depends on two variables. One is X, one is T. And this X, we can say that is represents the space. This T is represent the time. This U is can be temperature. So this function U is represents a temperature which is related to multi-variable X space T time. Okay, and you can think about this is a rod. Okay. And this rod has a heat transfer. So one of the tip of the rod is a cooling process, and the other tip of the rod is a heating. And there will be a heat distribution along this rod. And this heat distribution will be as function of space as well as time. Okay. And if you write as a PDE for the heat transfer of the rod, okay, so the heat equation we can write as the dot U over dot T. So the temperature as function of time is equals to alpha squared. It's a constant square, the du squared over dt squared. So the second, dx squared. So the second derivative of temperature as function of the space. And this is heat conductivity of a rod. And later we will derive these equations why we say this du over dt is equals to the alpha squared times the the second partial derivative of temperature as function of space. And the solution of a partial differential equations, okay, the solution of a PDE is the function u, which is as function of x and t, okay? So this is the definition of partial differential equations. And let's make some notations so that later if we write the PDE as those notations, you will be familiar with what we are talking about. So some notations. We use subscript to denote the partial derivative, the first order of partial derivative, okay? And we can use also ux, for example, how we use the subscript ux is equals to du over dx, okay? So this is the subscript, or we can also use uxx. That means the second order of partial differential of that function u as function of the space x. So it's du squared over dx squared, okay? So this is some notations we will use frequently for the following lectures. Then we can also write, sometimes I may use delta function to represent the derivative. So this can also write as u, du over dx. This will be delta square u, okay? So it's represent the second order of the derivative. Sometimes you can see the Laplacian operators, but we don't use in this class, so we don't introduce here. Then the next part, we will talk about different types of the PDE we will touch in these lectures, different type of the PDE. So we will introduce three types, three canonical partial differential equations. Okay, the three types we will involve 1, 2, 3. So we will talk about wave equations. We will talk about heat equation. We will also talk about Laplace equation. And as I introduce those equations, you can see either there is any similarities in between. Okay, so for the wave equations, we write as UTT is equals to alpha squared dot square u. Okay, so the alpha is some constant square. There's some constant there, and this is also the wave equation, also called hyperbolic PDE. Okay, the heat equation is UT is equals to alpha squared dot square u, and this is called parabolic PDE. Then the last type is the Laplace equation, which we can write 0 is equals to del square u. So you can see there are some similarities between the heat equations and the Laplace equations, okay? Because if my UT is equals to 0, then the heat equations will be the Laplace equations, okay? And you can also see some similarities between these three types. So these three types for the space part, the delta square u will be always the second order of the function u. But for the time variables, it starts with second order of the u as function of time. The heat equation is the first order of first derivative of u as function of t. Then the Laplace equations doesn't have the u function is not depends on the time, right? So we will make it a little bit simpler. As we said, this part, the right part, is represents as the derivative of the u function as function of space. Let's make a 1D space, okay? So 1D space, let's say 1D space. How we write 1D space? Let's say this 1D we represent x here. So how we write the wave equations in a 1D space? We can write UTT. So the left hand side is the same, will be equals to alpha squared UXX, because it's only at the dimension of x. So it will be the second derivative of x in the space. That will be the UXX. How you write the 1D for the heat equations? Simple. So it's UT is alpha squared UXX. Okay. So that is the 1D. And for the Laplace equations, let's write as 2D. Your 1D is not that meaningful. So let's write the 2D part, which will be UXX plus UYY equals to 0. Because we write 2D, let's say this 2D is x and y. So you will write UXX, which is the second order of the derivative of u as function of x, second order derivative of u as function of y will be equals to 0. Okay. And what kind of physics can derive these wave equations? Okay, can derive these wave equations. So one of the straightforward example of the physics will be the string. So think about if you have a string at this dimension x, okay, at this dimension x, if you pull out the string and if you release the string, then the string will be vibrate along this x dimension. So it will look like this. Okay, so it looks like a sine, or you can, if you release at different place, it can be a cosine function. It's really depending on how you refer to this x dimensions. So it can be the solution of the u function can be sine function at space dimension of x. And for the time, it also vibrates as a wave. So it's also a sine function or cosine function of time. So you can imagine this function u x t, because it depends on both the space and time, can be written as a sine x sine t function. Okay. And later we will talk about this wave equations using Fourier series, because you can see that this is related to some periodic functions, and we learn about the Fourier series. And this wave equation solution can also write as a sum of sine and cosine function. So that can be represented by our Fourier series. Then the heat equations. One example is very straightforward, can be a heat distribution of the rod. So this is a rod. Okay, this is a rod. And think about at time equals to 0, at the center of the rod, so T equals to 0, you add temperature here, a temperature source. Then the other part at time equals to 0 will be flight even here. Then at this point, the center of the rod will have this temperature T0 here. Then all the other will be, for example, room temperature there. Then as the time flies, the temperature will distribute through the rod as function of space, as function of temperature. Then it will look like this. So as T1, it can look like here. At T2, it can look like here. So it's distributes. This is T1, this is T2. It distributes like a Gaussian distribution. Okay, a Gaussian diffusion. Which can represent the temperature of the rod as function of time. So this is one of the examples for the heat equations, And for the Laplace equations, we write in the 2D format. And think about the difference between the heat equation and the Laplace equations is that this when ut equals to 0, from the heat equations that change to our Laplace equations. Okay, then what kind of system can have ut equals to 0? Let's make u as a temperature. What kind of temperature is independent of time? Then that can be the steady heat distribution. Means no time dependent. No time dependent and no heat flux. Or you can think about this rod, when the time going to infinity, then the temperature is all distributed through the rod, is not depending on the temperature anymore. Then that can be changed to a Laplace equations, which is only depends on the space. Okay, So that is different types of the PDEs. Then we will make each type of the PDE. We will give a physical model. We will derive the physical model to our mathematical PDEs. Then we will try to solve the PDEs. Okay. And another thing I want to mention that, so when we talk about ODEs, we always talk about this ODE has different types of the ODE. It can be linear or nonlinear, right? For the ODE. So nonlinear or linear. And that nonlinear or linear will directly decides whether this ODE can be solved or not. So analytical solve the ODE, we only learn about the linear ODE, right? So for these three types of the PDE, the wave equation, heat equation, Laplace equations, we found that the coefficient is either constant, right? It's either constant or it's all constant here. So it should be a linear, right? Linear PDE. It should be linear PDE. And when we talk about ODE, we also talk about different types, which is non-homogeneous, all homogeneous. So this depends on whether your ODE has forcing function or not. If the forcing function is 0, then you only have homogeneous ODE. Your solution will be only made by the homogeneous solution. If you have if you have a forcing function which is non-zero there, then it will be non-homogeneous ODE, and you will have both the particular solution as well as the homogeneous solution to construct the general solution, right? So for these three types of the PDE, what kind of is that non-homogeneous or homogeneous? If you see three types, we don't have the forcing function, so they are homogeneous. So it's linear homogeneous PDE for these three canonical PDE. And the last properties we can talk about is what kind of order of the PDE we have right now here. So when you talk about the order, we always talk about the highest derivative order of the function u. And for the wave equations, the highest order of the time and space should be the second order. So the same, left-hand side is second derivative of time. Right-hand side is second derivative of temperature. So this is second order PDE. Then if you see these heat equations, this is the temperature as function of time, which is the first order, but the right-hand side is the second order as function of space. So this is also second order PDE because we only see the highest order. The same thing for the Laplace equations, that is the second order as function of the space. So that is second order. So in summary, those three canonical PDE we introduced here are second order, linear, homogeneous PDEs. Okay.